All right, we are recording. Today is June 2nd. We're going to continue on with chapter 4. We'll then move on to the chapter 4 homework. So why don't we go ahead and do that? So I'm going to start sharing my screen. We left off yesterday here, so why don't we go ahead and start right here. And after we get done with this PowerPoint slides, or these PowerPoint slides, we'll take a brief break. I'll get the homework loaded, and during that time, you can go ahead and take a break. All right, so here we have the energy diagram showing us the most stable configuration for the cyclohexane. I'm going to get my pen out. You can see that we have the chair configuration as the most stable, and these half chairs are the most unstable. So most of the time we're going to be in our chair conformation. Here, remember this circle diagram right here? This is called your Newman projection. So they're giving you two Newman projections that represent this right here. And there's two carbons right here. If you look at this circle right here, there's going to be one carbon and then one carbon down that line right there. Then you got these two. It'd be two. This would be 3, 4, 5, 6. So there's 6 carbons in total in that diagram right there. So they're trying to show you, why this is the most favorable diagram, because we have all these staggered positions right here. And if we recall our energy diagram from the previous lecture just yesterday, we know that this is going to be the most stable conformation. So drawing the chair conformation, they're just trying to help you how to draw it. Let me see. You can pick whichever way you want. Takes a little bit of practice. I'm not the best at it either, but it's something like that. So go ahead and practice drawing it. I'll practice a couple more times myself. Everyone has, as long as you have 6 points, that's the main thing. And you're not going to be requested to draw these chair conformations in this class, but you probably should know how it's done. So let me try it one more time. Maybe I just start from the top. No, it's all the same thing. And those who are better drawers than me can probably do this a lot better than me. I'm not the best drawer. More importantly, though, the equatorial position is going to be coming out like, if we look at the Earth right here, this would be the equator, and this would be the equatorial position. And then, we have the Earth rotating on its axis, and this would be the axial position. So you're going to have some, hydrogens or substituents coming off in the axial and some coming off in the equatorial. And if this was a methyl group, you'd want it coming off in the equatorial position, because if you have it coming off in the axial position, you're going to have some repulsions right here. So there'll be more repulsions going on right there. If you have it in the equatorial, all kind of on its own, there'd be less of a possibility of these repulsions and interactions, so it'll be more stable. So if we have a choice to put the methyl group in the equatorial axial, we're going to put it in the equatorial position. And they're showing you, how to put these designators in. And if you start on this side of the chair, if you start up, the next one will be down, then up. It just alternate up and down. And you can see these are angled right here obtusely. And then you just continue the pattern around the cyclohexane ring. So if this was just cyclohexane, all these would be hydrogens. And the equatorial ones are shown in, this looks like a bluish green color to me. And the axial ones are shown in red. So when cyclohexane has one substituent, there are two possible chair conformations. And it can ring flip, and that's what happens right here. If this comes up, this comes down, and that's how you get this one to be in up position. This one can be in the down position. That occurs by rotation of all the carbon-carbon bonds in the ring. I have terrible allergies where I'm at right now. I'm in Iowa, so the funny thing is, I have my alarm clock set on Eastern time. I have my computer set on Eastern time, but I'm on Central time zone right now. But come next Monday, I'll be back in Kentucky. It says consider the methyl cyclohexane. So you can see if we put the methyl group in the equatorial position. Let's erase that. It's going to be 95% in that position, whereas only 5%, of the time, the methyl group will be in the axial position. So in the axial position, the methyl group causes steric interactions. And you can see that if we drew the hydrogens coming off this carbon, there's going to be more sterics involved than if they're just floating out in space amongst each other. So maybe not the best time to come to Iowa because I lived my allergies in Kentucky and then I'm reliving them here in Iowa. So, it happens. The steric strain from a substituent being in the axial position is the result of a 1,3 diaxial interaction. And you can see this right here. These interactions are going to be more likely. If we look back here, you're going to have your hydrogens coming up like this, right? And they're going to have more interactions, and they're not going to see that interaction in the equatorial position. That's all they're trying to tell you right there. And it says these are actually gauche interactions. Remember yesterday we talked about the gauche interactions, and that's from your Newman projections. And larger groups will cause more steric crowding in the axial position. So the larger group, the more sterics are going to be involved. When we look at the equatorial axial ratio, you can see that here's some type of it could be tert-butyl. This is a tert-butyl group where, let's go ahead and draw that on the previous slide. I'm going to erase some of this stuff. So let's just imagine this methyl group being a tert-butyl. Now we have this carbon, here's a carbon, here's a carbon, here's a carbon. Look at all the sterics involved. So wouldn't it be better to put that tert-butyl in this position? And that's what it prefers. And we can see that it prefers that position 9,000, almost 10,000 to 1. So with multiple substituents, solid or dashed wedges are used to show position of the groups on the ring. So solid means coming out of the screen towards you. The dash means it's going down into the screen away from you. In this case, I just want to take a peek at the next slide. In this case, this would be the more preferred way, and you have to always think about sterics. Let's just imagine if we put the chlorine here and the methyl group here. Well, we're going to have more steric interactions right here, aren't we? Yes, we do have hydrogens here, but those interactions are not going to be as much as if we have them right next to each other. I apologize. I need to step out. I need to go sneeze, so I'm going to step away. All right, I'm back. I'm sorry. Apologize for that. I couldn't function with these allergies I'm having. All right. We saw why the chlorine and the methyl group, if we have them in the equatorial position right here, it's not going to be as favorable because we'll have more interactions amongst each other. That's why we're going to put them in the axial position in this case. And they give you a practice. Now go ahead and you can practice this right here. All you have to do is draw the chair conformation and put the ethyl in the up position and the methyl in the down or in the equatorial position. Now, where the hydrogen is going to be right here, they're going to be here, and then they're going to be here like that. In this case, it'll be up. We'll have them some way to the. Like I said, I'm not the best drawer, but you know that's why they do have diagrams. All right, any questions on that? So there's two possibilities of the chair position. And here are your two chair possibilities. You have the ethyl group in the up position right here, and then you have the ethyl position in the side position here. If we draw, so let's think about this. If we have that methyl group there, we're gonna have a hydrogen right here. Hydrogen's there. And we'd have that hydrogen right there and right here. So who thinks number one is more stable and who thinks number two is more stable? I'm just curious. You know, let's kind of draw what this would be right here. So I'll just check the chat. You know, you can participate if you want. You don't have to. I'm just kind of curious what your thoughts are. Who decides number one and who decides number two? And, you know, most everyone's saying number two, and I'm going to agree with number two. And the reason being is, you know, that ethyl group is a whole lot bigger than a methyl group, right? Ethyl is 2 carbons versus 1 carbon. So it'd be better to have, you know, a constituent with 2 carbons. And let me erase, you know, I'm just going to erase everything. It'd be better to have a constituent with 2 carbons coming off than just to have 1 carbon coming off, because then we have more, you know, possibilities of interactions coming off. I'm not saying it'd be in this position right here, but you know, it is possible. So it'd be better to have that, you know, ethyl group coming off in the equatorial position. So it says, when naming a disubstituted cycloalkane, use the prefix cis when there are 2 groups on the same side of the ring, and trans when 2 constituents are on the opposite side. So here we have cis, same side, trans, you know, opposite side. And these 2 compounds are stereoisomers. Since they are 6-membered rings, they are best represented as chair conformations. So we put the trans in front, and then, you know, at the 1 position and the 2 position, we have 1,2 dimethyl cyclohexane. And this one, all we did was change trans to cis. So we have cis 1,2 dimethyl cyclohexane. So each compound exists as 2 equilibrating chairs, spending more time in the more stable chair conformation. So here are your 2 possibilities. Says decaline is a 2 6-membered rings that are fused together. You can see these rings hopefully 1, 2, 3, 4, 5. So that's what that is right there. So cis means on the same side, trans means opposite sides. And it says decline is a substructure is found naturally occurring in compounds such as steroids. You can kind of see if we just imagine, this structure or this structure coming over, we see this 6-membered ring right here in the testosterone. It says there are many important structures that result when more than one ring is fused together. Here we have bridging carbon right here, right? So here we have 1, 2. Here we have 1, 2, and here we just have 1. So that's how you get your 2,2,1 bicyclo 2,2,1 heptane. Yeah, this is just a common name right here, camphor. Here's another common name, camphene. So the structure of diamond is an of 6-membered rings fused together. So these are all composed of carbon. And that's it. So what I'm going to do is stop sharing for a second. So I'm resuming recording right now. We're moving on to chapter 4 homework. So if you can pull out your homework, if you're listening synchronously, if you're listening asynchronously, please pull out your homework too. The best advice I have is always follow along. That way you're not, going back and doing your homework again. It's always better just to practice it in real time too. So we have that. It's sharing my screen or not, but hopefully one of you guys tells me if we are sharing the screen. So I think I'm sharing my screen. So I'm not saying anything else. Let me just make sure about this. There we go. I think it was just sharing my name at first on the Zoom. So we have that. Okay, we got it now. So I'm going to pull off this keyboard. So chapter 4 homework, we're going to start with question number 1. So question number 1, they're going to have me draw a structure. I admit I'm not the best drawer. I don't have the best drawing skills. Okay, something like that. I try to draw the points to the best of my ability. So, let's just count how many carbons we have. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 carbons. So we're going to have, since this is we have a bridging carbon right here, it's not just going to be cyclooctane, it's going to be nonane. So we know we're going to have to pick nonane. And so if the option doesn't have nonane, you can get rid of it right away. They also give you a 3D draw or a 3D structure of this. So, and you can see that bridging carbon in that 3D structure. I'm just you can't see this, but I'm playing around with the 3D structure, and you should go ahead and try to do this. So if it says heptane, you're going to get rid of that. So you have how many possibilities? 1, 2, 3, 4, 5, 6. So still a lot of possibilities left. Now we need to see, how do we get to the bridge, we can go, so I'm going to circle this now, 2, 3, and then we're to the bridge. Here we have 1, and then here we have 1, 2, 3. So we're going to be looking for something that has a 3, 3, 1. So if you picked you'd be correct. So hopefully everyone saw how we got 3, 3, 1. Remember, in this case, we're going to put the 3, in front, because the larger number when we do these bridging, when we have these bridging carbons. I'm going to leave that up. I'm going to just take a glance at question 2. If you have any questions, just let me know. So 2, it shows us 2 compounds. Let's go ahead and draw these. I do prefer working on the PowerPoint slides as opposed to the whiteboard or chalkboard. It's just easier to erase and to to work with a digital board. I remember when I was in I'd even say college, our professors were still using projector screens. Or they'd take a piece of plastic and they'd write with a black marker on that piece of plastic, and that projector screen would project up on the board. This is much better. So we have to decide the relationship with these compounds, though. That's the question. So I need to study this before I make any definitive answers. And if you flip this, so I'll just call this one the left, and I'm just going to call this one the right. If you flip this right here, this stuff is going to come down, this stuff will come down, this stuff will come up, and you'll get the same compound. And this will be this stuff right here. This stuff will be this stuff right there. And this stuff will be this stuff right here. So it's the same compound. So you have to kind of visualize this in your mind, and you got to flip it. So flip the right one, and you'll see that it becomes the same structure. All right. So let's go to question. I'll leave that up while I look at question 3. So let's go to question 3. It says a 3-dimensional representation of butane is shown. Translate the information about the conformation of butane into its Newman projection and determine if this conformation represents a local energy minimum or global energy minimum. So Determine whether the conformation shown is the eclipsed or the staggered Newman projection and drag the groups to their correct locations. Leave the atoms in the wrong conformation blank. So really you gotta work with that 3D structure, to be honest with you. You gotta be able to turn that 3D structure. And when you turn it, you should get this methyl. If you look down, butane has 4 carbons, right? So for that first structure on the left-hand side, you know, if you have C1, C2, C3, and C4, I'm just labeling the carbons. Have it so that C2 and C3 overlap. So you want C2 and C3 to be on top of each other. You want them eclipsed. And then if you do that, you're going to find that that CH3 group is going to be on the left-hand side. And a hydrogen right here, a hydrogen right here. And when I eclipse them, you know, I'm going to try to draw this the best of my ability. You know, you're going to see that methyl group coming off right here. You'll see this other one coming out right here. It's a carbon, carbon, carbon. This would be carbon right here. These would be hydrogens. And then you're going to see something like, you know, you'll have this hydrogen be up, and you'll have another hydrogen down. So it is in the eclipse, so we're going to just keep it with the right hand, and not the eclipse, but it's the staggered. Sorry about that. So we have a staggered conformation. We're just going to leave it like that, because the right hand side shows eclipse and it's not eclipsed. So hopefully everyone's been able to see that, just moving the 3D structure around. So 4 says translate the given theoretical conformer from the Newman projection to its wedge and dash drawing. You might find it helpful to make a model to help visualize the different viewpoints. So this is where a model will come in hand. I don't have a model. We'll draw the representation to the best of our ability. So this is what they give us for the Newman projection. So let's see. And they want us to draw wedges and dashes. So if we draw, obviously that circle with the, that Newman projection represents 2 carbons. So we have 2 carbons right there. This fluorine will stick that fluorine up like that. Then if you turn the structure this way, imagine you turn that structure, and I don't even know how to turn it into the screen. That methyl group is going to go into the screen then. That bromine group is going to come out of the screen. And likewise, if that fluorine is, up like that, then the chlorine is going to be down. And that hydrogen is going to be coming out of the screen. And the OH group will be going back into the screen. So that's what they wanted right there. So hopefully that makes some sense. I'm just going to leave that up there so you can study it. And because stuff like this, you have to think about it in your mind, moving this 3D. Otherwise, it's just not going to work. So you see how you have this fluorine up right here. It's in the up position. This chlorine is in the down position. You had to move this methyl group right here. I'll put an X by it into the screen. So if you move it into the screen, you're going to have dash wedge. Likewise, if that's going in the screen, that bromine has to come out then, right? This is coming out. If that's coming out, it's going to be a solid wedge. Like I said, I'm just going to keep it right here because I know, it's sometimes difficult to visualize this stuff. So I want to make sure that you're able to do it. We're at 4, so we'll go to 5 then. Question 5 says, translate the given conformer from the wedge and dash drawing into its Newman projection. You might find it helpful to make a model, then manipulate it to the desired viewpoint. So it's this is question 4, but just flipped in the opposite, direction of what the question wants. So we have this. We have to project, or we have to select which Newman projection structure matches the conformer. So we're not going to be in the staggered position. And why we're not going to be in the staggered, this is eclipsed onto each other right here. You can see that, they're eclipsed. So we're going to pick one that has the eclipse form. If I look at the left side and we put the left side in front, then we're going to put this CH3 group here, followed by the chlorine right here, and the bromine. Then in the back, we'd have the hydrogen. That hydrogen, I'm going to call this hydrogen X, X. This will be Z, Z. That way you can tell which one is which. And then we obviously have that methyl group that we have to put, so we'll put that right here. So now you should be able to tell and see, why we chose what we did. All right, let's go to 6. It says isopentane, also 2-methylbutane. So, if we just, at the 2 position, there's a methyl group. Is a compound containing a branched carbon chain. A Newman projection is given for 6 conformations about the C2-C3 bond of isopentane. So we're talking about the C2-C3 bond right here. On the curve of the potential energy versus angle of internal rotation for isopentane, label each energy maximum and minimum with one of the conformations. So I'm going to get rid of that 6 because we're going to need this part. Thank you. No. So again, I try to draw it to the best of my ability. I have 1, 2, 3, 4, 5, 6. So an A, so A and E are going to be, let me just see something. We know A, C, and E are going to be staggered, right? You have A right here, C, and then you have E. These are all going to be staggered conformations, and B, D, and F, B, D, and F are going to be all eclipsed. So you can kind of narrow your choices down right there. So, B and D are going to be the easier ones. And that's going to have the eclipsed portion where the methyl groups are overlapping each other. So you're going to have 2 methyl groups eclipsed. And I'll just draw the methyl groups right here. These methyl groups are going to be eclipsed onto each other in B and D. So we have eclipsed methyl groups. F, it's going to be eclipsed, but the methyl groups are not going to be, right on each other. They're going to be on a hydrogen. So you'll have, and I'll draw 1, but you'll have a methyl group here. You'll have a hydrogen, and it'll just be, alternating hydrogen, methyl. So you'll have it eclipsed, but the methyl groups are not on top of each other like they were in B and D. So now we have 3 choices left. They're A, C, and E. We know they're all staggered. We have to pick the one So what we're going to do for C, we're going to pick the staggered one. Here's a methyl group. Here's a methyl group. And I'm going to pick the staggered one that has a methyl group right here, because that's going to be a little higher energy than putting the hydrogen right in A and B, and you're going to, or A and E, and you're going to see that. So in A, we're going to have that hydrogen coming here. Oh, that's really small. I'm going to have to get rid of that. It doesn't want to get rid of. Okay, there we go. So we'll put A over here. See that hydrogen right there? It's going to have less strain. And in this case, we'll put the CH3 here. And over here, we're just moving that CH3 group, but we still have that hydrogen coming down right here. We got the CH3s here, CH3s here, and the CH3 there. All right, so that's it. Does anyone have any questions on 6? I'll go in the chat. It seems like everyone got that one then. Seven. That says ID the most strained compounds. So just looking at, okay, so there's some different questions. So we have A, B, and C. So just looking at the structures, and I'm not going to draw all the structures, but just looking at the structures, you know, which one do you think has the most angle strain? And that's going to be the one that has a cyclobutane group. So you're going to pick the one with the cyclobutane group. I'm just going to draw it like that. And that's because if you recall, there's going to be more angle strain with the cyclobutane than cyclohexane. So you're going to pick that one. B says, which of these structures has the most steric strain? Now, if we're talking about sterics, then we have to look at all those methyl groups, you know, in the axial and equatorial position. And that's going to be the one with the hexamethyl cyclohexane. And that's due to all those methyl groups. So pick the one with the cyclohexane for B. And that's because due to all the methyl groups coming out. If we look at torsional strain, then we're going to pick the cyclobutane group again. We'll do one more and then we're going to take our 10-minute break. So for the substituted cyclohexane compound shown, identify the atoms that are trans to the bromo substituent. So, all right, so we'll go ahead and draw this one. We'll draw that one. So let's draw this. This bromine here. Chlorine here. OH. Chlorine. chlorine, CH3, hydrogen. So to identify the ones that are trans. Remember, trans means this, opposite sides. So if we look at chlorine, it's on the opposite side. Here's your chlorine, here's your bromine. If I'm looking at that, so you're going to pick C because chlorine is going to be, so you're going to pick C. Now, if we just see this hydrogen right here, that's that's not it. We're going to pick the OH. I want to put a check mark by the ones we're going to pick. So that's E. G would be the same thing, check mark. K, which is here, check mark. And H, which is here, check mark. So I will C, E, G, K, and H. These all have check marks. They're all trans. So like I said, we're going to take a 10-minute break. So if you have any questions, just put them in the chat. I'll get back to them after the break, and I'll see you soon. Thank you. Zoom recording. So we're back from our break now. Let's go ahead and share the screen. And we're working on question 9 now. Question 9 wants us to label each position as axial or equatorial. So we have a lot going on here. So let's go ahead and draw this. Oh, we don't want to go back to 8. Too bad. What I should do is just so I'm going to go ahead and start labeling when I put these in. This X right here, I'm just going to call it AX for axial. Y, this is going to be EQ for equatorial. And let's just go around. Then it wants us to label all positions that are gauche to Y, to the Y carbon on 1. So we will put, this is going to be an equatorial carbon right here. And it's going to be gauche. This will be axial. Q's could be better. Let me put that. This will be axial. Only supposed to see. I'm gonna erase that. That looks like there's two lines there or two carbons. So it's not. I know that's what it is. I'm gonna have axial and gauche here. I have equatorial and gauche. And here I forgot this one. We're gonna have a axial and gauche right here. So that's it. I'll go to 10. It says 10 for the substituted cyclohexane. They give you a substituted, there's fluorines, chlorines, some methyl group. Identify the atoms that will interact with the methyl group in a 1,3 diaxial fashion after rotation to the other conformation. So that means I won't be able to. So let me see. We're gonna have so right now we have it like this. I'm just going to draw the that CH3 group. So then it says we're going to have a ring flip, and I try to draw this to the best of my ability. So that CH3, you see how it flipped right there? Now it wants us to consider the 1, 2, 3 positions right here. So it'll be 1, 2, 3 right there. So these atoms will interact with the methyl in a 1,3 interaction. So that would be your C group. That'd be choice C. That C is right by that hydrogen. Let me see. The G, if we go this way, we come to G. And that's because these hydrogens are up right here. These atoms are up, so they can interact, in that direction after the rotation. And that's the only ones. So hopefully everyone was able to see that. $11. It says inspect the two molecules and consider which compounds contain the greater amount of gauche conformation for internal rotation about the central blue bond. And they give us choice. They show us this. And they show us this. So we have to think about which bond is shorter or longer. Bond shorter or longer. In this case, these bonds will be shorter. These ones will be longer. So the CO bond is shorter than the carbon-carbon bond. So the methyl groups of either A, the ether of A are closer together. So this is your ether group. So this is creating steric strain on the gauche conformation. This phenomenon results in less gauche conformation present for A. So there's going to be less gauche. So A has less gauche. And hence more of the gauche conformation for butane B. So we have so you can pick the one that has a CO bond is shorter. And this is due to, this ether group has electronegativity going on right here. It's going to pull in electron density here. It's going to create a shorter bond. What's 11? It says we have to draw two structures. One is the cis, the other one's the trans. So it says draw a cis 1,3-dimethyl cyclohexane. So let's draw. It's easy to draw the hexane group. It's just a 6-membered ring. Here's going to be cis. Here's going to be trans. In the cis position, we have the methyl groups coming, this would be cis, right? If we're on the same side, we have the methyl groups pointing up and they're on the same side. In trans, you're going to have the opposite side. Oh, I'm just going to use my eraser. In trans, we're on the opposite side. So we have to pick the opposite side for the methyl groups here. So in one instance, the methyl group's going down. In the other instance, the methyl group's coming up, with the hydrogens being opposite as well. All right, so that's that. I'll give you some time to make sure you get your drawings in right. We'll go to 13. It says consider the bulk conformations of 1,3-dimethyl cyclohexane. It says what structures represent the boat conformation for the cis isomers. So we have to pick the boat, and we're looking at cis, so that means they're going to be on the same side, right? So if we pick the methyl groups on the same side, we're going to pick A and D. Remember, the boat conformation kind of looks like this, right? So they're all boat conformations. We just have to pick the cis ones. We're going to pick the cis ones, with the same. Like I said, there's a lot better drawers than me out there. I should say artists. It is an art to draw, to be able to draw. All right, so that was 13. And the last homework question of this set is 14. We do have some time, so we'll go into chapter 5 a little bit. So it says, consider the isomers of tert-butyl cyclohexanol in conformational structures. 2 are cis-2 tert-butyl cyclohexanol and 2 are cis-3 tert-butyl cyclohexanol. Indicate which is the more stable conformation for each pair and indicate which of all 4 conformations is the most stable. So I'm just going to label my options. I'm just going to start top left. That'd be top right. This would be bottom left. That's how the questions appear. Select the more stable conformation of cis-2 tert-butyl cyclohexanol. We're going to select option A. Oh, didn't want to do that, but there you go. Oh. Then I'm going to move into the top right. It says select the more stable conformation of cis-3. So cis-3 tert-butyl cyclohexanol now be option C then. And then select the more stable conformation overall. The most stable conformation overall would be C. Check. All right, so I need to go ahead and pull up the PowerPoint notes real quick. See the mouse. I'm just loading up the notes for chapter 5. That's not the one. Here we go. I got chapter 5 now. I have to enable editing. I'm gonna have to reshare the screen because it doesn't. There we go. So chapter 5 is dealing with stereoisomerism. Isomers are different compounds that have the same formula. That's the key point. That's just something that you have to memorize. And it says there are 2 general types of isomers. You have constitutional isomers and stereoisomers. And constitutional isomers are the same molecular formula, but different constitution, so order of connectivity. And stereoisomers are the same molecular formula and constitution, but different spatial arrangement. So spatially, how are they arranged spatially? So remember, these are spatial, and this is a really good example. And, it says, although the 2 molecules below have the same connectivity, yes, they do. Here you have 1 and 2, here you have 1 and 2, but spatially, one's in the cis form, right? The other one's in the trans. So in order to give these compounds a unique IUPAC name, we use the word cis and trans. So we have cis 1,2-dimethyl cyclohexane, we have trans 1,2, and those are two good examples of stereoisomers where you have the same connectivity, but spatially they're different. Again, another example of stereoisomers where you have cis-2-butene and trans-2-butene. If we count this as 1, 2, 3, 4. So at the 2 position, you have a double bond and it's cis. And at the 2 position, you have a double bond, but this is trans to each other. So I'll let you go ahead and decide what you think they are. So, if you just flip this right here, you'll see it's identical. Here we have trans, here we have cis, we have our 2 stereoisomers. They're just different spatial arrangements. These are constitutional isomers. And let's go back and look at the definition of constitutional isomers. Same molecular formula, but different constitution, order of connectivity of atoms. So you'll see, and I want you to see that it does have the same molecular formula. Let's go ahead and do that ourselves. There's 2 hydrogens here. Each one has 2 hydrogens, so I'm just going to put 2s here. So how many carbons do we have? C, 1, 2, 3, 4. An oxygen, and how many hydrogens? 2, 4, 6, 8. C4O8, O8H8. Here, let's see what this one has. 4 carbons, 1 hydrogen. We have 3, 6, 8. 8 hydrogens. You have 3 here, 2 here. Again, you have 3 here. So that fits the definition of the constitutional isomer. These are identical because all we did was a ring flip. Likewise, right here, all they did was they rotated this. See that? There's a rotation here. They just kind of turned it. And a ring flip. So it's the same compound though. So hopefully you can see where these answers are coming from. So you had constitutional, you had stereoisomers, and you have identical. Again, let's practice it again one more time. Hopefully you came up with this. Actually, this whole, they have this wrong. So you have cis, trans, neither. I'm just gonna try to draw this. And put the hydrogen here. And if I flip it, I get the same thing. So that's why it's neither. This next slide is no good because it shows stuff from the previous question that we had. So I think this is a good slide to leave off. Remember to cross, some of these they had right, but some of these are showing from the previous slide, so I don't know why they're doing that. So there's your answers. Does anyone have any questions for me? All right, so that's a good point to do. If you're struggling with any of these concepts, please just go back and review them. Hopefully the homework will help out too. That's why the homework sessions are there. And just put a little bit of time into it. I have a homework assignment due myself today, 11:59 p.m. Nonetheless, it's 5 questions that I have to answer, and they're paragraphs regarding leadership traits. And I think it's been a good thing for me to study. It talks about being warm, it talks about relatability. So hopefully you have these warm relatability feelings when you're taking this class. I've struggled with this stuff in the past myself. When I was going over it, when I was at Iowa, I took this class back in 2001 and 2002. I think I took it in the fall of 2000 or spring of 2001, and then and then I took organic too in the fall then. But we've all struggled with this in the past. If someone says no, that's not true. The more repetitions that you do, the easier you're going to have, with these structures. And it's a good idea. I did have a molecular model set when I first went through this stuff, 20 years ago, I guess, and now it is. So if you can get a hold of a molecular model set, I highly recommend to get one. it'll really help you out with flipping these chairs like this. Otherwise, it's hard to visualize, to be honest with you. I mean, I know there's some 3D software out there now, but it was easier for me to visualize with a molecular model set. Maybe that's too old school now, and they do have, really nice 3D models for this. So that's my best recommendation.